In this video, we're going to do our first example using the conservation of momentum to solve an engineering problem. Here, you're a consulting engineer and you're asked to find the force needed to hold this large nozzle in place given the following conditions. We have an incoming velocity of 5 meters per second, the incoming area is 5 meters squared, and the initial pressure is 4 times 10 to the 5th newtons per meter squared. At the exit end of the nozzle, you have an area of 1 meter squared. I'm going to go through this problem rather pedantically to show you the steps and give you a recipe to really solve just about any problem you'll have in this class. If you follow these steps, you're more than likely going to get to a pretty close answer to the problem that you're working on. Okay? So, based on what we've already done in this class, you probably have a pretty good idea where we're going to start. So step one is define the control volume. Okay, so I'm going to go up here, I'm going to draw it. And again, we're always concerned with a good definition of our control volume. And a couple of things that we can notice here is we have two solid boundaries, so the flux across those boundaries is going to be 0, so that makes things a little easier. And our flow velocity is only in one direction, in the positive x direction. So if we draw a control volume that bisects this surface and then travels along the boundary of the nozzle, then comes across and perpendicular to this surface, and then comes back along the other end of the nozzle, then when we do our fluxes, because of the v dot dA term, we only need to worry about two surfaces, surface 1 here at the influx and surface 2 here at the outside of exit part of the nozzle. Okay, so now we've done a good job of defining our control volume. The next step, number 2, is to apply conservation of mass. Okay, so let's do that. So again, we write out our full equation for the conservation of mass in its general form. So we have d over dt times the integral over the control volume of rho dv plus the integral over the control surface of rho v dot dA, and the total change there is 0. Okay? We're given no information about the unsteadiness of the flow, so we can say that it is a steady flow, so this first term goes to 0. And then we can look at our two control surfaces. So we only have two surfaces that we need to add up. The flow is coming into 1, so by definition that's going to be a negative term. The flow is only in the u direction, and so we get negative rho u1 a1 for the mass coming in, plus rho u2 a2 for the mass going out, and that's going to equal 0. We can now rearrange that to solve for u2, the only unknown, and we get u2 is equal to u1 a1 over a2. Plug in our values there, we get 5 meters per second times 5 meters squared divided by 1 meter squared, we get 25 meters per second. Okay, so now we have u2, the velocity at the exit end of the nozzle. Okay, so we've done all that before. Here's where things get a little bit different. So now, step 3, we're going to apply conservation of momentum. Okay, so we're going to do the same thing. We're going to start with the general form of the equation. And here we're going to have the sum of the forces in the x direction, because those are the only forces that we have, is equal to d over dt times the integral over the control volume of rho u dv plus the integral over the control surface of rho u v dot dA. Okay? So we don't really know much about the sum of the forces yet, so we're going to leave that alone and deal with the other part of the equation. Just like before, we were told we're not given any information on the unsteadiness of the flow, so we'll assume it's steady, so we can get rid of this whole term. That's 0. And then we can start plugging in terms for the fluxes, just like we did for conservation of mass. So the momentum flux at surface 1 is going to be rho u times v dot dA. V dot dA is going to be an outward normal vector. And so that's going to look like this. It's going to be the sum of the forces in the x direction is equal to negative rho u1 u1a. Okay? And we're going to add to that the fluxes, the momentum flux at surface 2, which is going to be there. The v dot dA is going to be outward normal, so the velocity and the outward normal in the same direction, so it's a positive value instead of a negative value like the inflow. And we're going to have rho u2 u2 a2. So that should be 1. Okay? And we know all those numbers, so we can plug in. We're going to get equal to negative. The density of water is 1,000 kilograms per meter cubed times 5 meters per second squared, because there's 2 of them, times 5 meters squared, plus 1,000 kilograms per meter cubed times 25 meters per second squared, since there's 2 u2's in our term, times 1 meter squared. We plug that into our calculator and get an answer. This is the sum of the forces in the x direction is going to equal 500,000 newtons. And that's our answer for the sum of the forces in the x direction. Here I'd like to point out that for the momentum, we weren't able to get rid of the density like we did conservation of mass. And that's because we have things on the left-hand side of the equation that we haven't dealt with yet. So we actually have to multiply all this out and carry that density through. The second thing is that that's a really big number. 500,000 newtons is a lot of force. And that's kind of to be expected. We have water, which is a heavy thing. It's 1,000 kilograms per meter cubed, and it's moving fast. And so it's going to be a very large force. So that fits with our intuition of what the system's looking like. Okay? So step 4, the next thing we need to do is determine the forces acting on the control volume. Okay, we're going to determine the forces acting on the control volume. And here we're going to go back to statics. This is a statics problem now. The control volume is not moving. So let's do that. So here is our nozzle again, and we have our control volume is just like we defined it before. And since from our momentum analysis we already know that the only forces that we're dealing with are in the x direction, we'll draw a free body diagram for the x direction. Okay, so what are our forces here? Well, on this end we have the pressure, so a P1 times A1 to get a force. And then on this end we have P2 A2. Go ahead and draw our axes. So this is X and this is Y, like that. And then we also know that there's going to be some resulting force, and you can draw it however you want, but I'm going to draw it towards the left here. And this is the resulting force. And this is really going to end up being the force that we really want to know. So those are the forces acting on the system itself. And so we can now say that the sum of the forces in the x direction is going to equal negative Fr. It's our resulting force, and it's negative because of the direction that I drew it in relative to our axes, minus P2A2 plus P1, A1. Okay? So there is our free body diagram of the forces that we need to solve for. Okay? So step 5 is we have a situation where we have something we don't know. We need to determine P2 using Bernoulli equation. Okay? So we can set up the Bernoulli equation between the control surface at 1 and the control surface at 2. And that is going to give us P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. Okay. The elevation between the 2 points isn't going to change, so we can get rid of that. Z1 is equal to Z2. Z1 is equal to Z2. So we can get rid of the elevation terms. And then we know everything else except for P2, so now we can rearrange and plug in our numbers. So we're going to get 4 times 10 to the 5th newtons per meter squared over 9,810 newtons per meter cubed for the first term, plus 5 meters per second squared divided by 2 times 9.81 meters per second squared is equal to P2 over 9,810 newtons per meter cubed plus 25 meters per second squared over 2 times 9.81 meters per second squared. Like that. We can plug that into our calculator and get a solution, and we get P2 is equal to 1 times 10 to the 5th newtons. Okay? So we use Bernoulli equation here to solve for P2. Now we can directly put that into our sum of the forces. So now let's look at that. So now we're going to say the sum of the forces in the x direction is equal to negative Fr minus 1 times 10 to the 5th newtons per meter squared times 1 meter squared plus 4 times 10 to the 5th newtons per meter squared times 5 meters squared. Okay? This is newtons. Okay, so that's the sum of the forces in the x direction. We have that. That is equal to 500,000 newtons. All right? So now we can solve for Fr. So we can rearrange this and we get Fr resulting force is equal to 1.4 times 10 to the 6th newtons. And that is the force on the fluid. Okay? So that tells us that the force on the fluid is acting in the direction we ended up drawing it. If we had drawn it in the other direction, we would have ended up with a negative answer. So we have the force on the fluid is acting in this direction, and it's equal to 1.4 times 10 to the 6 newtons. So now we need to use Newton's third law and say that for every force there's an equal and opposite force to get where we need to go to see what the force we need to hold the nozzle in place. And so to get the force on the nozzle from the fluid, we say it's equal and opposite. So the force on the nozzle is equal to negative 1.4 times 10 to the 6 newtons. All right, so that's the force on the nozzle, and it's going to be acting in the negative direction, so in that direction. And then again, the force to hold it in place is going to be equal and opposite to that. So the force to hold is equal to 1.4 times 10 to the 6th newtons. And that's your answer. So, in this example, we used basically everything in our toolkit up to this point to solve an engineering problem. We started with conservation of mass, then we used conservation of momentum, then we used the statics to get our free body diagram, then we used the Bernoulli equation to solve for our unknown at that point, and then we went back to our conservation of momentum equation to get the ultimate answer. Okay, so we'll see you next time.